Hello my dear students, welcome back to the IMS GATE Academy. So let's continue the foundation course on the computer organization architecture. So in this session, I'll be continuing the main memory organization. In the memory organization, the topic is about cache memory. The last class, lecture number 5, we have started the cache memory design in terms of the cache organization, cache address mappings. From the cache address mapping, the first method, the direct address mapping we have seen. The implementation, the hardware implementation of the direct address mapping, let's continue in this session, followed by other two methods also we'll discuss. Fine. So what we discuss from the direct address mapping, so this method says, first thing you have to understand, the cache memory and main memory, both need to be organized in terms of blocks. Second approach, block of a main memory need to be mapped. Into cache memory by using function called k modulo n. So k modulo n is the function which gives the line number, block number in the cache memory. Line number or block number it will give, in that you can load it. So and also we have seen like the implementation part and also how to search the given address from the processor into cache memory. Those things we observed in the previous session. Kindly watch. So for this session prerequisite is what the lecture number 5 where I discussed. So let's continue. So look the point all of you here. So now whenever address comes from the processor CPU, that is address is what? Logical address. So this logical address need to be converted into physical address with the help of what? Memory management unit, right? So whenever this physical address comes, you have to search into cache memory. This is a cache memory. If the cache memory misoccur, we have to search into main memory, right? Main memory. Now how searching happens, I mentioned. Take this physical address, we have to divide it into 3 parts, right? What are 3 parts? Tag bits, followed by block number bits and word offset bits, right? The first step number 1, you have to take the block bits, block number. So block offset gives the block number in the cache memory. Find the block number. So concerned block, the tag bits will be the tag bits need to be compared with this physical address tag bit. This is a physical address tag bits. You have to compare. If the comparison success, if they are both match, we can say referred what is present in the cache memory. Otherwise it is miss. The miss case consequences will be you have to take the physical address, go to main memory, take the concerned block, again map, place into cache memory and restart the instruction. Fine, right? So now let's see the hardware approach, how this will happen. This hardware parts will observe. Now please understand. Look there clearly. Hardware approach to say it or miss here. The physical address, the same example I am continuing. Here. The physical address how much? 9 bits, right? Physical address is 9 bits. That is divided into 3 parts. Word offset. What is the block size I have taken? The block size, the cache blocks or main memory block size is 16 words I have taken. If the 16 words are there, how many bits required to address them? 4 bits required. So 4 bits required for this. How many blocks are there in the cache memory? 4 are there. So 2 bits required for this. 2 plus 4, 6. So 9 minus 6 is what? 3 bits for a tag. So 3 bits for tag. Now look at the cache memory. Cache memory having how many blocks? 0, 1, 2, 3, right? So binary address, if you write 0, 0, this is 0, 1, 1, 0 and 1, 1. Getting all of you. Look this now. How mapping occurs? K modulo n only. K modulo n need to be done, right? Now every cache block is associated with the tag bits, right? So let's say mapping happens, some blocks are there, assume that. So 10th block, where to place? 10. 10 modulo 4. So n number of blocks are how many? 4. So k modulo n, k is 10th block out of 32. Main memory contains the 512 words. I organized in terms of blocks. Same example which I discussed in the previous class, same example I have taken, man. No, nothing changed. There I took, no, the main memory size is 512 words, the block size is 16 words. So 32 blocks required to organize the main memory. The 4 blocks required to organize the cache memory, which I considered in the previous example. Now see here 10th block. So 10th block, where you know 10 modulo 4. 10 modulo 4 is 2. So block number 2. This is 10 here. Suppose 8 is there. 8 modulo 4 is 0. 8 will be here. 15 is there. 15 modulo 4 is 3. So 15 is here. 6. 6 modulo 4. 2 already there. Suppose if I take 5. 5 modulo 4. 5 modulo 4 here is a 5. 1. So these are the blocks presently available. Block number 8, block number 5, block number 10, block number 15. Now tag bits need to be updated for that, right? Tag bits. Tag bits need to be updated. What are the tag bits for that? Tag bits. Now see, what are the blocks are referring to this one? 0. Yes or no? If I write it, you know, here I will write. For block number 0, what are the blocks are referring? So 0 block, yes, 4 block, 8th one, 12th one, 16th one, 20, 24, 28, right? Yes or no? For block number 1 is 1, this is 5, this is 9, 13, 17, 21, so 25 and 29. For block number 2, this is 2, 6, 10, 14, 18, 22, 26, 30. For block number 3, this is 7, 11, 15, 19, 23, 27, 31. See. Now these are the main memory blocks which are referring into block. This is the cache block. These are the cache blocks. Right. There are 32 blocks are there in a main memory. 4 cache blocks are there. For each block of cache memory, 8 blocks are referring. Out of 8, 1 will be there, that we discuss. How to update the tag bits? 0 to this, how many blocks are there? 8 blocks are there. 0 position, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, like this, you understand. So that is the reason we require 3 bits, you know, 3 bits. Why? Because 7 or 8 are referring to maintain their addresses. So 3 bits required. 3 bits required. Now 3 bits I mentioned. Look here, 8th 0, 1, 2. So 2. This is 2 means how to write? How to write 2? How to write 2 here? So 1, 0. Sorry. Let me take. So 2, right? 0. So you see 0, 1, 2. 2 means what? 0, 1, 0. 0, 1, 0. Next one is 5, 0, 1. So means what? 0, 0, 1. First one. 10th, 0, 1, 2. So this will be 0, 1, 0. 15, 0, 1, 2, 3. So 0, 1, 1. So there are tag bits I updated here. I hope you understand the tag bits, how tag bits comes. You see how many blocks are referring? 8 blocks are referring. This is 0 position, 1 position, 2, 3, 4, 5, 6, like that, understand. The moment you load the block in the cache memory, tag bits need to be updated. What I said you steps, what are the steps I said you? The steps I said you have to take the physical address, divide into 3 parts, tag, block offset, word offset. So block offset bits, please understand. So the block offset bits, first you have to take the block offset bits. Now see the hardware component, all of you. As I mentioned, hardware component, first of all you need to search the block number. What kind of combination required, circuit is required to be enable the block number is, there is a multiplexer. See, now the 2 bits are there, control signals are 2 bits, okay. With the help of 2 bits, I am connecting the multiplexer. Multiplexer will select 1 block out of 4. So I used a 4 by 1 multiplexer. You see, 4 by 1 multiplexer is there, right? I hope it is visible. 4 by 1 multiplexer I used. Why 4 by 1? There are 4 cache blocks are there. So out of 4 cache block, 1 block need to be enabled. So with the help of, so 4 by 1 multiplexer require 2 control signals. I hope you know the functionality of the multiplexer. I hope you know the functionality of the demultiplexer, encoder and decoder. So 4-byte multiplexer require 2 control signals. Now see, so with the help of 2 control signals I can enable, this is the, this will come from 0, this is 1, this 2, this 3. Now how I connected? What I said is point. Take the block number bits, identify the block number and concerned tag bits you have to read it. How I connected, you see. Block number 2, right? Block number 2 I am interested. Okay, suppose block number 2 I am interested. Okay. So whenever this block offset bits giving suppose block number 2, assume sir, block number 2, then what to do? What to do? The concerned tag bits, so this tag bits you have to read it. Tag bits you have to read it. Okay, you have to read this concern and compare with the physical address tag bits. Compare the physical tag bits. So we need additional hardware components, comparator required. One comparator is required in case of direct address mapping. Sir, how one or why one only? Why not more? Since understand here, k modulo n function we use for the mapping. So k modulo n function gives a one location, exact one location. So that location need to be searched. So only one location need to be compared, not required to all, because we know k modulo n gives exact one location, right? So one comparator required. So what is this connectivity lines? Please understand. Why I place the 3 multiplexers? You see, there are 3 multiplexers I placed here. So multiplexer required to select one line out of 4. I selected, suppose. So by using combination 2 bits combination, I can select suppose block number 2. Once you enable the block number 2, that concerned tag bits you read it. So for that is the reason 3 multiplexers I read it. Why I place 3 multiplexer? Tag bits how many are there? 3. There are 3 tag bits are there, so 3 multiplexer. One multiplexer select the 1 bit only. So 3 multiplexers I place. So 3 bit data, no, here is a 3 bit data will come. One input 3 bit from here. Other input is 3 bits from what tag bits 3. So now 3 bit comparator required or not? So 3 bit comparator I place, 3 bit comparator. So one input from physical address tag bits, other input from the multiplexer, both will compare. So comparator will say whether hit or miss. Comparator is what detect the what? The comparator say hit or miss. If suppose both are match, it will say 1, otherwise 0. So this way we can understand. I hope you understand the point. How hardware is telling whether the block is present or not. How we can say whether the block is hit or miss by using hardware components. We need set of multiplexers and one comparator required. So requirements, if you see here, requirements, look all of you, what are the requirements I am telling you? Please understand clearly. Multiplexer, first component is a multiplexer required, multiplexer. So here are 2 things comes question number 1. What is size of the multiplexer required? Size of the multiplexer. Size of the multiplexer, please understand, depends on the number of cache blocks. So depends on the number of cache blocks. Number of cache blocks. Okay. How many blocks are there in our example? 4 blocks are there. So now 4 by 1 multiplexer is required. 4 by 1 multiplexer having how many signals? 2 control signals will be there, right? So now 2 control signals, suppose 0, 0, 0, 1, 1, 0, 1, 1 is there. Now see the 4 by 1 multiplexer structure, 4 by 1, okay. Now 2 control signals, let's say S0, S1, 0, 1, 2, 3, okay, it is connected like this, okay. Now based on this control signal, one line is going to be enabled like this, no, 0, 0, nothing but 0 line enabled. Suppose 1, 0 if I take, no, 2 line is enabled like this, understand. So now this line data will come out, multiplexer. So applications of multiplexer, if you see transmitter, so transmission and we use the multiplexer, receiving and we use the demultiplexer. So demultiplexer is opposite to this one, like, no. So like the receiver end, please understand, one line input, the 1 by 4, like, no. So 4 by 1 is a multiplexer, 1 by 4 is a demultiplexer. This is a, so you know this basics things, fine. Now size of the multiplexer depends on the number of cache blocks. So that is the reason I chosen 4 by 1, fine. Question number 2, how many multiplexers required? How many multiplexers required? Number of multiplexer depends on number of tag bits, please understand, number of tag bits, because ultimately tag bits has to come out, right? Ultimately tag bits has to come out. So number of multiplexers equal to number of tag bits. So kindly note of it, all of you, kindly note of it, the point here. What I am trying to say, simply, so I am writing, no, size size of the mux in this example will be n by 1. What is n by 1? Where n is a number of cache blocks. Next, number of multiplexers required equal to number of tag bits. This need to be note, all of you. This need to be note. Okay, important things here. Now third thing, so to say whether it is it or miss, so time for it, also we say it latency. So time for it or it latency. First, where you are searching? Multiplexer users. So time for multiplexer required plus. So multiplexer gives that we are connecting to a comparator. Time for comparator. So time for comparator. So this is a component which gives the how much time required to say whether the block is it or miss. Please see the diagram. See, first you are searching multiplexer. You see with a block offset you select the one block out of and read the tag bits compared to the comparator. This will say whether it or miss. I hope you understand how this is it or miss. Please. Now what I can do, I can take the example here. I can take the example. Look the example. Suppose example if I take, okay, I want to read it. No, I want to read the word number. I want to read it. Suppose let's say what are the blocks are there? 8, 5, 10. This no, the 15 is there, right? So now suppose, so block number. Suppose example I want to read it. Example, let's say I want to read it. I am writing the word number 510. Assume that I want to read it word number 510. Whether it is present or not, we'll see. Word number 510, whether it is present in the cache memory or not, we'll observe. So what I said you, for this 510 you have to write the binary address, right? So 9-bit address comes, right? How it will come from CPU? Sorry. So if I want to write it, properly, see. CPU generate the logical address for word number 510. So that need to be converted into physical address. Okay. So physical address came for word number 510. So decimal. In binary, this done by what? Memory management unit only, right? Yes or no? Now see. So 510. So how to write the decimal address? Binary address 510. So 512 position I should not make. 256 1. Then 250 is 128, I will take 1. Okay, 128 I will take 1. So now see 511 is, so like suppose whenever 9 bits are all are I, if 9 bits are all are I, so 511 can I get it or not? 2 power of 9 is 512, so 0 to 511, right? Now see that I have to subtract 1. So this I will take it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, 10. So 9 only required, right? 9 only required. Okay. So look it clearly, all of you. 1, 2, 3, 4, 5, 6, 7, 8, 9th bit. I'll take it 0. Okay. So this is the 1, 2, 3, 4, 5, 6, 7, 8, 9-bit address came. 9-bit address came. I hope you understand this point clearly. 9-bit address only. So total how many words are there in my program? You can also check. 512 words are there. So for physical address 9 bits required. If all 9 bits are 1, the last word will come. So last word will come or not. So we need not 511, we need what? 510th. 510th means the last bit is 0, last word. Chalo. Now we'll do it something. Okay, what can be done? This need to be divided into, so this need to be divided into 3 parts. 1, 2, 3, 4. 1, 2, 3, 4. Okay, this is a word offset. Then this is what? Block offset. This is block offset. So these are the tag bits. These are the tag bits. Okay. So these are the tag bits now. Please understand. So these are the tag bits. Look. Now see, the tag bits are there. Okay. So what I said is step number 1. Step number 1, take the block. So block offset bits. That is block of 1, 1. Okay. go to cache memory. So this block offset means, so this 1 is given to the multiplexer, right? Multiplexer will select the third line or not. See, go and see. When I give block offset 1 so 1 nothing but this will activate. So this will activate, nothing but this tag bits will come out or not. So this tag bits will come out. So this tag bits will come out here. So 0 1 1 will come. So what is second step I said you? What is second step? So now this multiplexer given 0 1 1 it is given, because 0 1 1 given. Then what is next time? So 0 1 1 came. Now this 0 1 1 you have to compare. So this 0 1 you have to compare physical address tag bits. Physical address tag bits. Physical address tag bits. Okay. So what is the physical address tag bits? 111 is there. 111 is there. This 111. You have to compare these two things. Will it same? No. This comparison not match. So not matched. Not matched. Please understand. So not matched means what? So what I can conclude? Hence, the referred word. So referred word number. So what is number? 510. 510 in decimal is not present. Is not present in the cache memory. In the cache memory. So this is a conclusion. Now what is the solution I have to do? If the word is not present, block is not present. The solution is hard. Take the physical address, go to main memory. Take the physical address, go to main memory. So concerned block, again you have to map K by using K modulo N and restart the instruction, then definitely it will be 8. So this way it can be done of this approach. Chalo. We'll see some some problem we can observe here. We can see the problem, but before that, what I can understand, what is the advantage of this method? What is the advantage of this method? Please understand, it is simple to implementation, and implementation cost also low, is low in cost. And in terms of performance, if we see, this is a slower mechanism among three. Among three, this is the slowest one. Why? It has a problem, it is produces more conflicts. What is the conflict we'll observe? What is the conflict we'll observe? What is the conflict we'll observe? Okay, look this point. So the direct address mapping is exposed to conflict penalties. Hence, so it's the slowest address mapping scheme I mentioned. What is the conflict penalty we'll observe? Okay, look this point. Look the point here. I am taking an example. Consider main memory size 1024 words, cache memory size 64 words, and block size is 16 words I have taken. During program execution, CPU is given the following reference to cache memory. Assume that cache memory initially empty. Now references are like this now given. Okay. If I execute these references, let us observe how the direct address mapping is performing. How the direct address mapping is performing. Now see what the cache size they said. Cache size is 64 words and block size is 16 words. Now I want to know number of blocks. So number of blocks in cache memory. So cache memory equal to. So 64 words by block size is 16 words. So that will be 4. Understand now 4 cache blocks are there. 4 cache blocks are there. Block number 0, block number 1, block number 2. So I am writing block number 0, block number 1, block number 2, block number 3, which are initially empty. They said, no, I have considered, assume cache memory initially empty. Now reference comes from the processor what block number 4. See, and let me write here references. So references block number 4, block number 8, block number 4, block number 8, block number 12, block number 20, 24, 4, 8, 24, 4, 8, 12, 20, 24, 12, 20, 24, 12, 20, 24. Yes. So these are the references. Observe. So initially cache memory is empty. Okay. Block number, referring the block number. This is the reference to the block numbers. Fourth. Here 4, 8, 12, 20 indication of block number. So how many blocks will be there in the main memory? 1024 words. So one words. One block size is 16 words, 1024 by 16 words. So number of blocks, I can write number of blocks. So blocks in main memory equal to 1024 words by 16 words block size. So this 2 power of 10 by 2 power of 4, that is 2 power of 6. 64 blocks are there. In a main memory, 64 blocks are there. These 64 blocks are mapping into 4 block of cache memory. This example which I consider. Now see, the reference goes for block number 4. So we are going to search into cache memory. So block is 4 is not there because empty. So can I say this is miss or not? This is miss, not there. What is the solution? Go to main memory, take the block number 4, map it. So direct mapping, right? Now 4. So number of blocks, how many are there? 4. 4 modulo 4, how much? So k modulo n nothing, 4 modulo 4. What is 4 modulo 4? 0. So nothing but in this position you have to place it 4. Yes. So after some time the reference goes to block number 8. So is it there block number 8 in that? No. So this is also missing. M is miss here. What to do again? 8 modulo 4 you have to do. 8 modulo 4, 0. But 0 location, what happened here? Already block is there. Then what to do? Simply remove this block number 4 and place it 8. That need to be do. So restart the instruction and fetch instruction from main memory and executed. After some time reference generated for the next block, that is 12. Is it 12 is there? No. That 12 is there in main cache memory? No, empty. So that is also miss. So what to do? 12 modulo 4, 0 means again you need to be forcefully need to remove the block for 8 and place 12. So now after some time reference goes to block number 20. Block number 20 is not there. So the block number 20 also miss. Now 20 modulo 4 is again 0. Remove 12, place 20. Next reference goes to 24. 24 is not there. So this also miss occur. 24 modulo 4. Again what? 0. So 0 remove. 20 remove, place 24. Now reference goes to 4. So 4 happened miss or not? This miss we consider as a conflict miss. We called CM is conflict miss. Conflict miss. What is the conflict miss? 4 is not coming first time to the main cache memory. 4 already was there. First time we referred. There are 3 types of misses will be there. One is compulsory miss, one is conflict miss, one is capacity miss. I am writing here. One is compulsory miss. Compulsory miss. Second one is a conflict miss. Conflict miss. I hope you understand. Third one is the capacity miss. Capacity miss. There are 3 types of miss will be there. Conflict miss, compulsory miss and capacity miss. So please, capacity miss generally happens due to size of the cache memory. Compulsory misses means compulsory because when cache is initially empty, the first time when you load a block from main memory to cache memory is a miss only. The first time is access required, right? First access is a miss only. When the cache is empty, when you start execution, you are trying to search the block that will be miss. So first time you have to fetch from main memory only, right? This is the compulsory misses. Conflict misses will happen due to the function. How, sir? See, block number 4 initial which we placed in the cache memory, but that was replaced by 8. Why we chosen 4 to remove placing the 8? Because of function, not because of the cache memory. So we have empty places or not? See, we have empty places. Still we remove the block number 4 and place 8. It is not because of the capacity miss. It is because of function. Function says k modulo 1, giving that block number 0, you have to forcefully place in block number. This is the meaning of conflict miss. Conflict penalty means conflict happened, penalty extras. Now see, the 4 got miss occur, right? 4 got miss occur. Then again we have to fetch a block number 4 from main memory or not. So this is a penalty, means extra time required to fetch a block number 4 from main memory because of this function. I hope you understand. Anyway, I can understand here first time 4, 8, 12, 20, 24 which are unique blocks only. First time which you fetching, the miss happened. It can happen with any method, that is okay. But the 4 again miss occur. It is not because of the size of the cache memory, it is because of the function. Now 8 also miss occur, 8 also miss occur, this also conflict miss, right? Conflict miss only, why? Because first time we brought but replaced by 12. So 12 also what happened? So this also miss, conflict miss, right? So now when 4 miss occur, 4 modulo 4 0, remove 24, place 4. Now referring for 8, so 8 is not there, remove 4, place it 8. Then when you are referring for 12, remove 8 and 12, place it. Then next will be the 20, 20 is also not there, remove 12, place 20. So this also miss, this also miss, so this also miss. So remove 20, place 24. So what I am saying, how many misses happen? How many? So miss, how many misses happen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Suppose miss rate, if I ask you, what is the miss rate of the cache memories? In this case is 100% only, right? Yes or no? Every reference miss occurred. Is it because of the less size of the cache memory? No, because not able to utilize the cache memory properly. That is the biggest drawback from the direct address mapping. All of you please understand. It is the biggest drawback from the direct address mapping. Clear? So now how we can overcome this one? How we can overcome this one? Please. Suppose simple statement, if I say, instead of choosing this block only, placing the blocks, these are the blocks. If I say one simple statement, place anywhere, will it improvise? Let us observe. So I am saying that take this cache blocks only. Okay, 1, 2, 3. Initially empty, right? 0, 1, 2, 3. Okay. Initially empty. This is a cache memory. Suppose simple statement, if we say the reference comes, choose any cache block. Choose any cache block for loading. Choose any free cache block. First reference comes one. What are the references? I am writing 4, 8, 4, 8, 12, 20, 24. 12, 20, 24. 4, 8, 12, 20, 24. 4, 8, 4, 8, 12, 1, 2, 3, 4, 5, yeah, 10, right, correct. Okay. Now see the first reference. What is the first reference? The first reference is what? 4, 4. The cache is empty. This is miss. So I'll place it here. So next reference goes for 8. This also miss. What I'll place it here. I am saying one statement called place any block of main memory into anywhere. Wherever empty block is there, cache memory, you can place it. If I say this statement, whether it will implement or not, we'll see. But will improvise or not, we can observe. Yes, I placed here. So this also miss occur, I placed here. Okay, this also miss occur, I placed here. Getting my point? Suppose this also miss occur, so I placed here. Assume that. Getting my point? So this also miss occur. So this 24 is there, 24 now is there. You check it. How many size? 16 words are there. During program execution, CP given or like, yes, okay. Okay, 24. Now 4. So 4 miss occur. 4 is not there. Okay. So now the 24 reference goes to 24. 24 miss occur. Suppose I remove this 20 and place 24, assume that. Now understand, 4 is there, right? So 4 is there, we call it. 8 is there, 8 also 8. 12 is there, 12 also 8. 20 is there, so 20 is miss. So suppose I remove this one and placed 20 is here. Now 24, so 24 is present it. So this way we can understand. Now it is improvised or not. Yes, some problems will be there, but it is improvised or not, because you see number of its how many? 1, 2, 3, 4. 4 out of 10, almost 40% improvised. 6 misses are 1, 2, 3, 4, 5, 6 are there. 1, 2, 3, 4, 5, 6 are 6 miss. The 4 its are there. Then you can ask me question, sir, instead of this replacing 20, if you would have replaced 4, 4 replaced, you place 24. So replace 4, remove 4 and place 24. Then this 8. So 4 is going to miss, 8 is going to miss. So that we can work out with the replacement policies. Better replacement algorithm, if we use it, choosing the blocks for removal, so then definitely we can improvise this approach also. What I am trying to say here, direct mapping, direct address mapping having the limitation. What is the limitation? So this giving the function k modulo. Because of this function, more conflict penalties have happened. So this conflict problems can be avoided, saying that place a block in cache memory wherever it is free. So that method is called, we discuss what, associative or full associative mapping. So we can discuss that one. Let's first see some problems on direct address mapping. Suppose if I consider cache memory, of 64 KB, block size is 32 bytes. Okay. CPU generate 32-bit address. So CPU generate 32-bit address. Consider cache memory as 64, block size is given 32 bytes. CPU generate 32-bit address. Find the tag bits, word offset bits. Block offset bits. So this is a question. Okay. How we can attempt? You see now, all of you. How we can attempt? We'll have seen. Now what is the cache memory size? Cache memory size 64 kilobytes. Okay. Now what is the block size they given? Block size is 32 bytes is given. Fine. Please understand, all of you. Now what they are asking question? Tag bits, word offset, block offset they are asking. So now if you observe the direct address mapping, the physical address, how physical address is partitioned? The physical address is partitioned to 3 parts, right? Tag bits and block offset bits and word offset bits are there, right? Tag bits, block offset, word offset. So to answer this question, first of all, I need to find out the number of blocks in cache memory. Number of blocks need to find out, because block offset value depends on the number of blocks only, right? So number of blocks in cache memory need to be find out. How to get cache size? What is cache size? 64 KB divided, what is the block size? So 32 bytes more. How I can do 64? We can express 2 power of 16 bytes divided by 2 power of 5 bytes we can express. So 64 is 2 power of 6, 1 KB, 2 power of 10, 2 power of 16 by 2 power of 5. So this gives the 2 power of 9. So 512 blocks are there. Getting my point? If 512 blocks will be there, please understand, if 512 blocks are there, so block offset value gives, 9 bits required for this. Since there are 512 blocks. Word offset depends on the block size. What is block size? 32 bytes are there. 32 bytes are there, right? 32 bytes. So 32 bytes nothing but 5 bits required to address them. Now what is the physical address they said? They said, CPU generated 32-bit address. 32-bit address, right? So 5 plus 9, how much? 14. So 26 plus 2. So 14, right? So the 16 plus 2, 18. So 18 bits for the tag. I hope you understand. They ask find the tag bits, word offset and block offset. Word offset depends on the block size. So please note of it, all of it clearly. Word offset depends on the block size. Block offset bit depends on the number of blocks. So number of blocks are 512 here, 9 bits required. The tag bits we can get it. So subtraction of the physical address minus these two components, you will get the 18 bits. So 18 plus 5, 23. So this 23, 7 if you take this 32. Yes, correct one. I hope you understand this point. Let's take another question. You see the another question, another example. Consider a cache consisting of 128 lines with a line size of 64 words. The CPU generated a 20-bit addresses of a word in the memory. The number of bits in the tag, line and word fields are respectively. So see now physical address, how much they given? 20 bits they given. So this physical address is divided into 3 fields, right, under direct address mapping. So tag portion will be there, followed by block offset portion and word offset portion, right? So please understand, all of you, this word offset depends on the block size. Please look at the block size. So this depends on the number of blocks in cache memory. N is the number of blocks in cache memory. So this depends on log of main memory blocks divided by cache memory blocks base 2. Either you can do this way, or physical address minus these two components also can remove it. So this is the way we can get it. Now see, so cache consists 128 lines. Please understand, nobody should confuse with the lines. Line nothing but cache only, please. Sometimes the question they can see lines, line or block. Please understand, block. All are same. Line nothing but block only, please. How many blocks are there here? How many blocks are there? 128 blocks are there. They said 128 nothing but, now tell me the block offset will be what? 7 bits or not? 7 bits only. Log of 128 is 7. Now what is the size of the line? Line size nothing but, see, block size. What is the block size? 64 words. Block size is 64 words. So log of 64, this gives us 6 bits. So can't we find this tag bits now? Tag bits can't we find? 20 bits minus this 2 only, right? So this is 7 plus 6 is 13. So 7 bits is the tag, right? So answer is what? Tag is 7 comma, line is what? 7 only. 7, 14, 14 plus 6. So this answer. This would be one of the option we can understand. I hope it is clear. Direct address mapping. Now let's look on to the, so next approach is what? Associative or full associative mapping. Associative or full associative mapping. Because I said address mapping schemes are 3: direct address mapping, associative and full associative. And third one is what? Set associative. Let's work on the second approach, is associative or full associative. What was the limitation of the direct address mapping? What was the limitation of the direct address mapping? Conflict penalty. The disadvantage of the direct address mapping can be overcome by using the what? Associative mapping. What is saying? Permitting each main memory block to be loaded into any line of the cache, any line, nothing but any block, anywhere you can store, wherever free blocks are there, so you can place it. Means simply I am rewriting the statement. Any block of main memory can be placed anywhere in the cache. That's it. This associative mapping is saying that. Now look this. So if you place anywhere, so searching will be difficult. How to search? How to search important. See what I am saying. The cache control logic represent the physical address. Now two parts are there. Now function is not there. Please understand. So now see, in direct address mapping, physical address divided 3 components, right? Tag, block offset, word offset. So there is no function k modulo in case of full associative. Now so the address having only 2 parts only. That is tag bits and offsets only, nothing else. So the tag field should be the tag field uniquely going to identify the main memory location. The tag bit fields uniquely identify the block of main memory. Means, so I'll show with the example, you will understand. So the unique, please, by using tag bits only you can identify the what block number of a main memory. Please understand. Now see, so do determine whether block is in the cache memory or not. The cache control logic must be simultaneously examined every lines of the tag for a match. Since we are placing anywhere in the cache, every cache block need to be examined. So now cache controller tag simultaneously search every block parallelly. Every block you have to search parallelly. So wherever it is present, it will be match. Then we can say it is it, otherwise miss. So there is a simple concept, hence, so number of comparators equal to number of cache blocks required. In case of direct address mapping, number of comparators only 1, because we know the location k modulo n is the location where I kept my block. But here we don't know. You can place anywhere. So if you say you place anywhere, every cache block need to be observed. So every cache block need to be compared with the tag bits. That's the reason number of comparators required in this case will be n, where n is called number of cache blocks. Hence, so this approach is complex, please understand. So associative or full associative mapping is complex approach. This is a complex one comparison to direct mapping, but it can be faster. It can be faster. Chalo, we'll observe the things here. Okay, look all of you. So let me take the with example only. Let's understand this concept by using example only. Look all of you. Consider cache memory of 64 words, comma, main memory of 512 words. Same example I am considering, and block size is 16 words. Word length is 16 bit, assume that now. So now if I ask question number of blocks in cache memory, by n I am representing. Cache size 64 words divided word length how much? 16 words. So this giving the 4 cache blocks. This gives how many blocks? Like 4 blocks. 1, 2, 3, 4. 0, 1, 2, 3. Okay. Similarly, number of blocks. So that I am representing m in main memory. Equal to main memory size 512 words divided by what is the cache block size? 16 words. This gives 32, which are numbered from 0 to 31. Please understand. Now, if I ask question, what is the physical address here? The physical address always respect the main memory size. So what is the main memory size? 512 words are there. That's 9 bits. Please understand. So physical address is the 9 bits here. How arrangement goes? Please observe all of you. How arrangement goes? We'll observe. Okay. So this is the main memory. Okay. This is the main memory of 512 words. Okay. How we organize? Block wise. Block number 0, block number 1, block number 2, block number 3. Like so block 0, 1, 2, 3, 4. So 31 blocks are there. Number of blocks equal to here 32, which are 0 to 31. The cache memory, what is the cache memory here? The cache size, what is the cache size? The cache size is 64 words only, I said, right? 64 words. 1, 2, 3, 4. Okay. So block number 0, block number 1, block number 2, block number 3. Now how mapping goes here? No function, no k moduli, and you are using no function at all, please. So this is not there. It is only applicable for a direct address mapping. In this case, any block, anywhere you can place it, anywhere in the cache. Anywhere in the cache is a line, please understand, this is a line. Anywhere in you take any block of main memory, place anywhere in the cache. Wherever empty block is there, you can place it. Fine. So now see, we'll observe clearly. Here mapping we'll see, as well as how searching also happens, we'll observe clearly, please. Suppose 0. So 0 block I want to place it. You can place anywhere, not necessary here. You can place it here. Suppose I want to place 10th. Yes, you can place 10th. So 10th block I can place it. Here 5th one you can place it. 4th I want to place it. 15th I want to place it. I placed here. Please understand. So since here also, please, every cache block having the tag bits. Every cache block has tag bits. Okay. So this tag bits. Okay. Now see. If I ask a question, how many blocks are referring to this location? How many blocks? All are referring, right? It can be all. So block number 0, please understand. You can place 0 or 1 or 2 or 3, 31, right? So 0, 1, 2, 3, all, it can be 31. Out of 31, you can place any one, right? So in block number also same, 0, 1, 2, 3, up to 31. For block number 2 also 0, 1, 2, 3, 31. So block number 3, 0, 1, 2, 3, 31, please. Now this tag bits must be unique, right? Please. If it is duplicated, you cannot search it. The tag bits must be unique here. Out of 31, you can refer, out of 30, you can refer here 1 you can place it. And remaining 31, you can place 1. Remaining 30, you can place 1. Remaining 29, you can place 1, like this, understand. Now, what are the tag bits goes here? How many bits for a tag? How many bits for a tag? How many are referring? All are referring. So now all are referring means how many? 32 are referring. So 5 bits required. So now 10th, right? 10th. 10th will be the position number. How much? 0 is 0, 1 is 1, 10. So 1 0 1 0. I'll write it. Yes or no? 5. So how many bits? 5 bits required, right? So 0 0 1 0 1. 4 0 0 1 0 0. Right? This is 3 2, right? 15 0 1 2 3 4. 15th. So tag bits you see. So total how many blocks are? 32. 32 unique addresses are there or not? 32 unique addresses are there. So whatever block is there, that address only I am writing here. That number only I will, that is a tag bits here. This is what placing. Simply take a block, any block, you find the empty place, load it. And whatever the block number you place in, that number you have to update here, tag bits. 15th block you place, 15th number enter. 4th block place, 4th number. 5, 5, 10, 10 you have to update it. This is what mapping. I hope it is clear, all of you. So I hope it is clear, the mapping mechanism. Simply place it anywhere. Let's see how searching happens here. How searching happens here. The question is that how to search a block. How to search a block in cache memory. In cache memory. How to search a block in cache memory. How to search a block in cache memory. Look, all of you. Whenever the process, let's say process PA is running in CPU, we generate the address. This address we call logical address, right? So this logical address we convert into physical address with help of hardware component memory management unit. You have to take this physical address, go to cache memory, search. If it is present, given to the processor. If miss occur, you have to search into main memory, right? Okay. Now this physical address, right? This is a physical address, the physical address. Okay. So this physical address, now in case of direct address mapping, physical address divided into 3 parts. Now how many parts this should be divided? It is only 2 parts now, please understand. 2 parts only there. One is tag, other is word offset. That's it only, tag and word offset. So why so it is 2? Why it is 2 if the question? Simply please, I don't know, like where I place, right? Are you getting? I am not giving an address where the block is placed. So no need to maintain the block number where you place. No need to search the block number where you place. You have to search all of them. You have to all of them search. So that block offset will not be there. Simply total tag bits only. Now in this example, physical address almost 9 bits, right? So now what is the block size? What is the block size? So block size is 16 bytes, nothing but 4 bits. So now tag bits will be 5 only. 5 bits will be the tag bits. How, sir? See now 32 are mapping. So 5 bits only we got or not? 5 bits. 5 bits. Tag bits are 5. And word offset bits are 4. 5 plus 4, 9 physical address. Now address is split into 5 bits. The tag and word offset. Now please understand. So these tag bits, how searching happening? Tag bits need to be compared. Physical. This is a physical address. Physical address or tag bits now. The physical address tag bits need to be compared. Please compare with tag bits of cache memory. Tag bits of cache memory. We have to compare parallelly. All the things you compare. Wherever it will be matched. So that will be it. Otherwise miss. Let's see the diagram for that. Let's see the diagram for this. You see now. In this example, I am taking physical address how much? 9 bits only, right? 9 bits. Okay. So this field is divided into 2 parts. Word offset and tag, right? Tag. Look this all of. Word offset required how many? 4 bits. Same example, tag bits required 5, right? See, I have taken 512 words main memory. 512 words main memory, total 32 blocks are there. Cache memory size of 64 words. So number of blocks how many? 4. You see the tag bits. So tag bits 5 is required or not? So I am taking, like, suppose this example I will take it. What I stored here? 10, 5, 4, 15, right? 10, 5, 4, 15. Tag bits is what? 1, 0, 1, 0, right? 0. 0, 0, 1, 0, 1. 0, 0, 1, 0, 0. 0, 1, 1, 1, 1. Right? These are the tag bits. So these are tag bits. Now, what I said, you first you tag bits take. Okay. So tag bits of physical address need to be compared with every tag bits of the cache memory. That is, there is a comparators I place. No, 5-bit comparator. Why 5-bit comparator required? Why I mentioned? Because tag bits are 5-bit comparator required. How many comparators I placed? 4. Why? There are 4 cache blocks are there. We have to search every cache block because we don't know where we kept. Every block need to be searched. Now see how I connected. See, 5 comparator I place. For the comparator, 2 inputs will be, 1 input from physical address, other input from tag bits cache line. This line is connected. This line is connected here. This line is connected here. This line is connected here. Now comparator will give 2 things, either 0 or 1. Please understand. 1 means if match occur 1, 0 means not match occur. So now see, so 4 lines are connected to OR gate. One of the line will be 1, all are 0. So this will show either 0 or 1. OR gate says that it or miss. Getting my point, all of you. OR gate gives either 0 or 1, nothing but whether it or miss it will give. So this, so in this way, what hardware help is required? No multiplexer requirement, we need comparator, heavy comparators required. If 1024 blocks are there, 1024 comparators required. How many? 1024 comparators required. Plus 1 OR gate is required. That's why I said you, it is costly. This approach is costly, but it's fast mechanism, because in case of full associative mapping, no conflict penalty. Conflict penalty will not be there. Fine. So now let's observe how searching example, with example we'll see. Searching part with example we'll observe now. Getting all of you? With example we'll see. Suppose processor, look all of you, CPU, okay. This is a process A who is running in a CPU. The process A having the 512 words, it generate the address, okay. Let's say logical address, right? So this logical address need to be converted into physical address by memory management unit. Suppose this address comes for 162, assume that. Let's take now 165. Word number 165. This is the decimal. So binary 165, how to write? In binary 165, how to write? 165 means 128 position is 1. 128 plus, should I take 128 plus 30, 64? 64 if I take, it will be large. So 64 is 0. 32 I can take. 128 plus 32. So this is 0. This one is 160. 160 only, right? 160. So 32 is so 32. 16 0 8 0 4 2 0 1. Yes. 1 2 3 4 5 6 7 8. So I have to pad 10 here. So 9-bit address comes. Now physical address, see. From process, physical address is 0 1 0 1 0 0 1 0 1. This is the address. Okay. Address. How many bits address? 9-bit address. Now this is 9-bit address side. 9-bit address. 9 bits are there. What I said you all of you? What I said you all of you? Yes. This address need to be divided two components only. What are 2 components? Tag bits and word offset. Word offset how many required? 4 bits. 1 2 3 4. 4 word offset. So these are tag bits. Tag bits how many are there? 1 2 3 4 5 tag bits are there. Please understand. So you have to divide. What is step number 1? Simple step number, right? So this physical address, right? This is a physical address. Physical address tag bits. Okay. Tag bits. Okay. So need to be compared with need to be compared with what? So cache block, cache block tag bits. You have to compare. Okay. All, please understand, cache block tag bits means all cache blocks. All cache blocks you have to compare. So how to do? Please understand. Here is 0 1 0 1 0. Okay. So now see the first one, 0 1 0 1 0, right? 0 1 0 1 0. Is it same thing? 0 1 0. Yes. So what is second block? So 0 0 0 0 1 0 1. Third block is 0 0 1 0 0. Fourth block is 0 1 1 1 1 is there. Who is matched? This is matched, right? So this is not matched. These are not matched. Now see, understand, matching occur or not? This is matched. Matched. So what is the point I can conclude? The referred word number by the processor, okay, whatever number 165 decimal is present in the cache memory, So this way we can tell. Yes, I hope you understand how to search. How to search part is important, ma. How to search? Well, how to search, ma? Simply I said you take the address, divide into tag and offset, tag bits compared to every cache block tag bits. Then if it is matched, fine. Otherwise, we can say it's not there. Fine. It is miss. If miss occur, take the physical address, go to main memory. So there you split block number offset, take the block number, place it anywhere in the cache. So what are the observation we can make? Full associative, please understand. So time for it. Will be, okay. What are the components are involved here? Comparators plus OR gate. So all comparators are running parallelly. So comparator delay plus time for OR gate. This is the it latency. Second observation. So now number of comparators, how many? Number of comparators equal to number of cache blocks n. Please understand here, this is important. Third one, size of the comparator. Size of the comparator is what? Number of tag bits. So this is the important points need to be noticed. In case of direct address mapping, number of comparators will be only one. In this case, we'll have number of cache blocks. This observation. Now we'll see one question from this area. Consider main memory size 8 GB. Cache memory size is 64 kilobytes. Block size is 32 bytes. Assume byte addressable memory. Calculate number of bits for tag, block offset and word offset for the direct mapped and full associative cache, followed by size of the cache directory in bits for the both mapping. They are asking extra thing, cache directory also will observe, okay, will observe. But in this case, they did not give the physical address. Physical address need to be calculated. We need to calculate. Look carefully, all of you. So given things will take. What is the main memory size? Main memory size is 8 GB. Byte addressable memory, they said, right? Byte addressable memory. If main memory is 8 GB, so we can get the physical address. Log of main memory only I said you. Okay. This is log of 8 GB. How to write this 8 GB? Please understand, all of you. Log of 2 power of 8 means 3. GB means 30. 33 base 2. So 33 bits is the physical address. So 33 bits are physical address. We got a physical address. So in case of direct mapping, if you want to find out block number or tag number, anything, we need number of blocks, right? So now first of all, need to calculate number of blocks in cache. So that I am indicating by capital N. What is the cache size? Cache memory is 64 kilobytes. 64 kilobytes. What is the block size? Block size is 32 bytes. So 32 bytes. So this we can express 2 power of 16 bytes by 2 power of 5 bytes. This giving 2 power of 9. So 9 means 512. 512 blocks we got. 512 blocks we got. Right. Now first one. So direct mapped cache. So what is the physical address we got? Physical address is 33 bits. This physical address is divided into how many parts? 3 parts here. Tag, right, plus block offset followed by word offset. Yes or no? Yeah. Yes, tell me, word offset depends on what? Word offset depends on block size. What is the block size? So 32 bytes means 5 bits required. So block offset depends on number of blocks. 512 blocks, 9 bits required. So 9 plus 5, 14. So means 6, 16 plus 3, 19 bits for this one. Answer is 19 comma 9 comma 5. Right? Similarly, second question, second part. For associative, full associative, they are asking. Associative address mapping. So in case of associative address mapping, physical address divided into this 32 bits divided into 2 parts only. Yes or no? What are the 2 parts? Tag is there, that's it, and word offset will be there. This word offset depends on block size only. Word offset depends on what? Block size only. What is block size? Block size is 32 bytes means 5 bits required. For a tag, remove 5 from 33. So this 28 bits. 28 bits for a tag. This need to be understand. This need to be understand. And another question they asked, size of the cache directory. They are asking cache directory. So need to be understand here, what is a cache directory? So this cache directory, please understand. Also sometimes they are asked, so metadata for cache. Metadata for cache they can ask. Or metadata for cache controller. All the terms are same only. What is the cache directory size? Observe clearly. This is a cache memory. Cache memory has set of blocks. Let's take 4 blocks are there. Every block having the tag bits or not? Yes or no? Every block having the tag bits. Okay, this tag bits will be there. Tag bits will be there. Now see, understand here, cache directory size nothing but need to find out the size of this tag memory. Also sometimes they ask tag memory only. Simply they can ask tag memory also they can ask. Tag memory, metadata for a cache, cache directory size, all the terms same. So size of the tag the memory need to find out. How can you get it? So this tag bits are for every cache block. Here 5 bits are there. Here 5 bits are there. Every cache block has 5 bits only, right? Yes or no? Please understand. If 5 bits are there for a tag, so multiply by the number of cache blocks or not? Yes or no? This need to be calculated. Look this. For a direct mapping. So for a direct mapping, okay, directory size if you see. So in case of how many bits we got tag for this here? 19 bits, right? 19. So 19 bits for each block. What is the block? How many blocks are there? So 19 bits into 512. You multiply, you will get this answer. Now associative mapping. Associate mapping case of same, directory size equal to tag bits into number of cache blocks. Tag bits how many we got? 28 bits into number of cache blocks are 512. This is a tag memory. What they are trying to access this, see, size of the cache direct in bits they are asking, both the mappings. Yeah. So answer is what? This answer both the case. Okay. So now I hope you understand the full concept of the direct address mapping as well as a full associative or associate mapping. So next method is the set associative. So I'll discuss the set associative method into the next upcoming session. Thank you so much.